Hello everyone, welcome to the second day of the third AOGS-EGU Joint Conference for Natural Hazards in Asia. And thanks for joining us today. I hope you enjoyed interesting discussions from Theme 1 and Theme 2 yesterday. And today we will bring more interesting discussions from Theme 3 and Theme 4. I am Phạm Tiến Đạt, speaking to you from Hanoi, Vietnam, and I am convener of Theme 3, Natural Hazards in Megacities. A little bit about myself. I'm from Vietnam National University, Hanoi, and I'm working on coastal hazards, including sea level changes and other extreme events around the Southeast Asia. But I'm not alone today, as there are two other conveners who are together with me in this session. Let me introduce David Hickett from UK. Good morning, David.
Morning. How are you?
Can you have
good to see everybody?
Hello.
Hello, Fei. Professor Fei Chan from China. Thank you very much. As you know, megacities are defined as cities of more than 10 million people. And according to the UN, the megacities are more vulnerable to natural hazards. Megacities, however, are very different in economic size, different in physical and physical-social complexities. Therefore, there are a number of questions about how megacities are impacted by natural hazards, or how to bring scientific results into real action, or what we can do to build more resilience for megacities to natural hazards. So to address those questions, we invited here today three special guests who have been working on this topic for years or even decades. So I am very pleased to introduce you to our panelists of Theme 3. So we have Professor Nguyễn Hồng Quân from Institute for Circular Economy Development, Ho Chi Minh City, Vietnam. We have Professor David Chen from the Chinese University of Hong Kong, Central China. And we have Dr. Andreas Speyer from British Geological Survey, UK. Now, I would like to invite our panelists to step into the virtual stage and have a brief introduction about yourself. Professor Quân, would you mind to introduce yourself first? Yes, Professor Quân.
Hello, everyone. Can you hear me?
Yes.
Okay. Yeah. Thank you very much, Dr. Dat, for your kind introductions, and thank you very much, the conveners, for having me today in the panelists. It's my great honor to share some of our work on most likely on urban flood related in Ho Chi Minh cities, but also I put into the context of urban resilience and sustainability. My background is environmental hydrology by trainings over the last 15 years, working especially in Vietnam, but also in collaboration with colleagues from the Netherlands, Germany, and other countries. And over the last 2-3 years, I'm also shifting a bit my work from water management or water resources governance into a bit broader in terms of circular economies. So, but of course, water is still one of the core of my current study. So I'm very pleased to be here today and looking forward to sharing with you all. Thank you.
Thank you very much, Professor Quân. Next, we will hear from Professor David Chen.
Hello. Hello, everyone. I'm David Chen with the Chinese University of Hong Kong, currently in the Shenzhen campus, and also I've been affiliated with the Department of Geography and Resource Management at the Chinese University of Hong Kong in Hong Kong for over 20 years. And I am a hydrologist and a climatologist. I have been doing research in mostly in southern China, in the Pearl River Basin, Pearl River Delta region, the megacity region in southern China. Now it is called the Greater Bay Area. Over the years, doing research on water resources management, hydrological processes and changes, and also the water related hazards, including flooding, droughts, and storm surges in the coastal cities in southern China. Nice to join this wonderful group, and interesting way to communicate with colleagues around the world online. And thank you for inviting me to join this section. Thank you.
Thanks a lot, Professor David Chen. And Dr. Andreas Peo, please.
Hello everybody, and thank you also for inviting me to be a member of this panel. I am the head of the Coastal Geohazard and Resilience at the British Geological Survey. So my expertise is on coastal morphology, disaster risk on coastal cities, but I'm going to be talking about something very different today. And the main reason is because we realize that to actually have an impact and to translate our geoscience into more secure or reduce disaster risk on coastal cities around the world, you need to bring the social aspect. So I'm going to be talking about two particular projects. So the Alliance for Urban Resilience in Southeast Asia, and about the other project on the Royal Society, about how do we understand the root causes of disaster and how the social part makes a very big part of those. So thank you very much. Looking forward to the discussion.
Thanks so much, our member of the panel. Now, I would like to have guidance for the audience throughout this 4-hour meeting today by sharing some slides so that you can easily follow our schedule, right? So as you see on the screen, you are in the plenary session now. And after this session, Team 3 will have 2 breakout discussions, 1 and 2, starting from 1600 to 1730, right? So in breakout discussion 1, we will talk about some current trends of natural hazards in Asian megacities, and presented by Professor David Chen from the Chinese University of Hong Kong. And following that will be breakout discussion 2, with the topic of the resilience and possible interventions of megacities to the occurrence of natural hazards. And we have 2 speakers in this session, Professor Nguyễn Hồng Quân and Dr. Andreas Peo. And after breakout discussions, we will have the 30 minutes to view display material from Team 1 to Team 7. And the last hour of today will be the keynote talk for Theme 3 and Theme 4. And audience, you can see the links provided in the box chat, or you can go to the link that I put on the screen at the bottom of the screen here, tinyurl.com/HAZE-program2021, and you can choose the link to join the breakout discussion with us. Now, for this meeting, as we want to produce more interactive discussion together with breakout discussions, so we did create Padlet discussions so that the audience and participants can leave their comments, their ideas and opinions there. And in the Padlet discussion, we proposed some guiding questions and some discussion points, and feel free to express your opinions. And we think by doing this way, we can build up more meaningful ideas for future. And instead of just listening to our panelists, now you can provide some meaningful ideas for based on your own research in your own country. So the link to the Team 3 Padlet you can find on the screen, tinyurl.com/Team3 Padlet, or you can use the QR code at the right top corner, so you can access from your smart devices. And if you never used Padlet before, so I think that will not be a problem, because it's quite straightforward to leave your comment based on the instruction on the screen. So if you want to add comment, just click on the blood signal and you can enter your name and your country, so we will know where you are from, right? And use the vertical scroll button to go up and down in the column, because we put there some materials for your information. You can read some links to Dr. Andres Payo projects about the hyper expanding cities. I think it's very useful material to read, right? And and back to our plenary session. Now, I would like to ask our panelists for very brief viewpoint on the topic. So you can share with us what you want to talk today, or what you think about this topic, and what the main points you would like to discuss in the breakout discussions. So Professor David Chen would like to go first, because you'll be the first presenter in breakout discussion 1. Professor David Chen, please.
Okay. Now the theme of our this panel is natural hazards in mega cities, and we are going to talk about the trend. I think given the climate change at the global scale, and also the regional scale, and also the land use and land cover changes driven by a wide variety of human activities, including urbanization and the urban population growth and economic, socio-economic development. And the more and more people live in the coastal cities. Say, for example, in the coastal regions in the east and southeastern part of China, and also other parts of the world. And more people and more academic, more wealth are exposed to the threats of natural hazards. So this kind of pressure imposed by the more frequent and more intensive events, weather events, extreme weather events have been increasing. So we have been doing research in this area, as I introduced myself earlier on, and especially in the Pearl River Delta region. Now it is called the Greater Bay Area in China, in southern China, covering about half of the Guangdong province, including 2 administrative regions of the People's Republic of China, Hong Kong and Macau, plus 9 major cities, including 2 mega cities in the region. The 2 mega cities are Guangzhou and Shenzhen, and we have 70 or close to 80 million people living in this region, and the only a very small portion of the Chinese territory, and but it produces about up to 15% of the GDP, and so this is a clear indication of the concentration of the economic activities of wealth and also people. So I'm going to later on talk about a research that we have done and published. We published the paper in PNAS last June on the greater flood risk as a result of the slowdown of tropical cyclones over the coast of China, especially in our region, the Greater Bay Area region. I think I'm going to stop here and let other panelists to speak first.
Thank you, Professor David Chen. I think we have plenty of time in breakout discussion 1 to discuss in more details on the trend of natural hazards in mega cities. And I know you will take some examples along the China's coast, right? Okay. Thank you very much. Professor Kwon, do you want to add something on this topic?
Yeah, thank you very much, Dr. Dat. Also, thanks for James for previous sharing. Yeah, I think it's also saved a lot of my effort because I'm not really expert in climate change related projections, and also, of course, there are different, physical characteristic or can be included in the future scenario in terms of water management and climate change. My talk will be more on maybe a bit local implementation perspective from Ho Chi Minh cities, where I'm trying to share what my talk and also our current study about how to translate maybe like science into practice, which is by building consensus amongst different stakeholders, how local governments or other industry partners can support the, let's say, solution proposed by professional or academy. And also, given my recent work on circular economy, I'm looking on more integration perspective. So we are going to solve natural hazard. It's not alone, but it's not to be incorporated with different aspects. So I'm also looking forward to share the sharing from Andres, because I think our work also very related to social science, especially perspective from different stakeholders, building consensus to implement integrated solution. Yeah, thank you.
Oh, that sounds very interesting, Professor Kwon, and I look forward to seeing your talk in breakout discussion together with Dr. Andres Peo. Andres, I know you have some projects in the hyper expanding cities in Southeast Asia. What do you think?
Thank you, Dad. I guess probably my highlight will be that that hazards are natural, but disaster risks are socially constructed. That will be my highlight. We are very comfortable as geoscientists on understanding the natural hazards, but we are less comfortable looking at the socially construction of disaster risk. So I'm going to be talking about how can we bridge these two fields that tend to be separated, and that's the two projects that I'll be talking about. Why do we focus on hyper expanding megacities? Because those are places where planning has been outpaced by growth. So when you look at how the megacities are growing, they grow much faster than planners can actually plan and develop the growth. So we need to understand how megacities growth. That's part of the socially constructed. And also we have to understand that different cultures perceive risk in a very different way. So I'm going to be talking about a bit of the role of culture, how risk is perceived. And at the end, hopefully I will make you all feel a bit uncomfortable for the reasons that I explained at the beginning. So we are moving away from geoscience and entering the social science realm. But I think it's a necessity. So we need to, if we want our research to actually have an impact on the ground, making more resilient cities in the future, we need to understand how social science work, and that's what I'm going to be talking about.
Okay. Thank you, Dr. Andres. You mentioned about the different cultures. What do you think whether it's challenge for your work?
I see culture is what I'm seeing clearly as the most difficult thing. If you look at the same event, a flooding event in the UK, Hanoi and Manila in the Philippines, how is perceived and how the culture react and respond is very differently. And understanding the culture and how can you embed the solution in that culture, that's a key thing for me.
Thank you very much. David and Faye, do you want to add something for, and I want to ask quick question for our panelists. We still have 10 minutes to go.
I think today is very good. So David, I'll just speak first, and then as far as I hope today, I think one of the very important message is we have a lot of expertise, and then David is here, Andrew is here, and then also all expertise is here. And then I think my question is we need to, if we through today, if we can have any very in-depth discussion on understanding about the current major impact, and then any urgency that we can actually discuss to suggest something to make forward, especially in light of the COP26 is upcoming in Glasgow very soon. So I think the message is like, how can we address something that to bring back home and to the audience as well. Thank you. David, I'll pass to you.
Okay, thanks, Faith. I'd like to invite our audience to engage with the panel today. We have a variety of ways of being able to do this. Dat has introduced the Padlet. What we really like people to do through the day, I was going to say morning because I'm in the UK, but afternoon if you're in Asia. What we'd like to encourage is for examples of work that people are doing to go onto the Padlet. Later on in the sessions, there'll be opportunity to ask questions directly through the chat, and in the breakout sessions as well. We can even have people speaking their questions. So the aim of this meeting is really to encourage interaction. I think for many of us who've been in virtual meetings rather than real conferences over the last 2 years or so, it's that ability to talk to people that we're really missing. So we're trying to create an opportunity here to get that discussion flowing. So please be enthusiastic to post your examples, ask lots of questions. This theme is particularly interesting just because of the enormous increase in urbanization around the world. So it's now thought that 55% of the world's population is in urban areas. By 2050, that's going to be projected to be 68%. So understanding the interactions of natural hazards and social systems, I think, is incredibly important, and I hope we'll get some interesting ideas of ways forward today. Okay, thank you.
Thank you, Faye, Jan, and thank you, David. If I would like to, one would like to see some question from the audience. If you have the quick question for our panelists before we handle, we have to show, we turn to show to team 4. We have some few minutes to go, and I would like to see whether any question, quick question from the audience. So if not, I think this ends theme 3 plenary panels. We will see you again in breakout discussions 1 and 2, starting from 1600 to 1730. And now the audience can choose for interactive discussions and topics. You can see the links which is provided to you in the box chat, or you can go to the link on the screen and select the link for theme 3 or theme 4. So a little bit ahead of schedule as we have a few minutes to go, but I think it is time to handle our session to convener of theme 4. And I think goodbye for now, and we will see you again very soon in breakout discussions. Okay, so convener of theme 4, if you are ready, over to you.
Good day to everyone. Good afternoon in East Asia, and good morning in Europe. We are here now to introduce with some minutes in advance the team 4. I will share my screen in order to better show to you the plan of this session related to remote sensing. So the team 4 is mainly based on monitoring and remote observation. We already proposed this topic last year because it is a hot topic related to natural hazards. We will have 30 minutes to discuss, but before the short invited talks, I would like to give a very quick presentation about conveners and the invited speakers. So I will start with myself. I'm Paolo Taroli from University of Padova. Please, Nelly, Philippe, introduce quickly yourself.
Hi, all. My name is Nelly. I'm from Indonesian Agency for Meteorology, Climatology, and Geophysics.
Hello, everyone. I'm Philippe Jousset. I'm at GFZ Potsdam in Germany. It's morning here, and it's very interesting to be here. I'm very happy to welcome everyone. And then Niels, unfortunately, has some duties at the GFZ and could not come, but he has the full trust of us to carry on with this theme nicely, and he would like to excuse himself. Okay, so now maybe Sabine, Eva, and Gilda can introduce quickly themselves.
Yes, but I'll go first. Good morning and good afternoon, everyone. My name is Sabine Chabrirat, and I'm a professor in digital soil mapping at the University of Hanover and at GFZ in Potsdam. And I'm a specialist in hyperspectral remote sensing. Thanks.
Hello, my name is Eva Eibel and I'm based at the University of Potsdam. I'm a professor of general geophysics and I will talk about seismology and rotational seismology today.
Hello, good morning to everybody. I am Gilda Currenti from INGB Catania in Italy. I am a geophysicist involved in geophysical application for volcano monitoring, and my talk today is about fiber optics.
Okay, thank you to the free invited speaker. I wish you remember that you will have a maximum 8 minutes to give your presentation, to share your screen. And after this 30 minutes presentation, we will have the breakout discussion. The breakout discussion is structured in 3 stages. Remember, you need to use the link of Zoom. You're looking at the text to join it. So we will organize a 3 stage. The first one is related to remote sensing discussion with some question related to the opportunities and the cost and limitation of remote sensing. The second one is about in situ census discussion, also in this case cost and limitation in conducting in situ analysis and the survey, and then there will be the last session on future of remote sensing. And then at the end of this we will have a breakout again 30 minutes altogether session, and then we will introduce the keynote speaker at 6 p.m. in Asia and 10 p.m. here in Europe. So we can start. So I will stop now the share to share the screen, and I think Sabine, you can start your presentation.
Thank you, Paolo. It's nice to meet you. By the way, after so many virtual conferences. So, can you tell me if you see my screen and the presentation in presentation mode?
Yeah.
Perfect. Okay, so great. So first, thank you for Paolo and the conference organization for inviting me to give this talk. It has been actually very interesting to prepare these slides for me. So I'm going to speak about spectral approaches and the potential of the Nmap spaceborne hyperspectral satellite for natural hazard monitoring and research. And we are located at the GFZ in Potsdam, and I'm also at the Leibniz University in Hanover. So first, a very short introduction in hyperspectral remote sensing. So what we call with that is those new advanced optical remote sensing sensors that instead of having 10 to 15 spectral bands like Sentinel-2 or Landsat 8, multispectral satellites, here we have a satellite that will acquire more than hundreds of narrow contiguous spectral channels. And thanks to these contiguous spectral channels, I'll use them as a pointer, yes. Basically, you have access to this contiguous signal here. And for example, when you are looking at soils, you can look at the graphs on the right. Basically, you see all these ups and downs in the signal, and they are really directly related to soil composition. So for example, if I look at this signal here, I can see there is some clay in these soils, there is some organic matter, some iron oxides, and this signal has also been used to quantify the amount of soil moisture in the top, in the surface of the soils. So the advantage of this technique is that it has got the potential to identify material composition and to quantify also the different surface materials at the surface. So yeah, let's go to the next one. So basically at GFZ, we are the science principal investigator of the future EnMAP satellite. So the EnMAP mission is for environmental mapping and analysis. It's a global coverage mission, so it can acquire over the whole globe, 30-meter pixel size like Landsat, 242 spectral channels. So here you already see, so we will have a big data volume. This data means also big data volumes because every image is times 242. So this means also the revisit time is not as good as multispectral satellites, it's 27 days. So the key goal of the missions is measurements of surface biophysical and geochemical parameters. What is nice is that it will be coexistent with Sentinel-2 and Landsat 8, also flying at approximately the same time. And something important also that the acquisition is on demand. So because of the data volume, this cannot be like Sentinel-2 and Landsat 8, that it acquires the whole globe the whole time. So if you want an image, you have to ask it. So it's a German project with a core project from the German research, finance and open data policy for scientific users, and basically launches next year. So we are really looking forward to it. So we identified the main application fields for the EnMAP mission, and you see in the center here, very important, natural hazards. So actually hyperspectral, I think, can provide its own contribution to natural hazards in different applications that I will speak a bit more. And in particular, we identified two questions where hyperspectral can in particular help, like which areas are to what extent vulnerable to natural and man-made hazards, and also in case of a disaster, which areas are and to what extent affected, because this is where hyperspectral can really provide something. Some more words. As I said, the main benefits is the potential for a more differentiated characterization of the predisposing factors in terms of different soil conditions, different vegetation conditions, different soil moisture conditions, basically the nature of the surface of the Earth. And it's also a potential for a more differentiated characterization of changes after the event in regard to the environmental conditions and the affected infrastructures. So we had a list that if you are interested to read more, I enjoy you, I put the link here to look at the EnMAP science plan, where all these applications are detailed and where we see that it can bring something basically for landslides and improved characterization of the predisposing factors. For swelling soils, actually from the mineralogical differentiation, we have a direct identification of soil potential hazards, if the soils are exposed at the surface, of course. Then for floods, we can monitor surface soil moisture, water quality changes, and some soil contamination also. For drought and land degradation, it's a large potential because it detects the state of the vegetation and also soil conditions. For volcanoes, there are different studies that look at various crater types, lava flow types, volcanic deposits, and also like for heavy metals, like mining waste, plastic waste, pollutants. This capability of identifying the material has shown to be very important. So I just very quickly wanted to show 3 examples that we worked especially at GFZ. So on landslide, for example, on the right, it shows a current basically study looking at remote sensing based landslide analysis using multispectral time series data. And you see it was focused on southern Kyrgyzstan. All the landslides could be identified and also multi-occurrences. So for example, this is something that can be done now, but when we look at spaceborne hyperspectral benefits, what we can do is, for example, better differentiate lithological conditions, or also look into the maybe slope-prone or landslide-prone slopes, and see if we identify homogeneities in the vegetation cover or in the soil moisture. And basically, the idea is that we could have better characterization of what could be active unstable slopes, or also potential for better prediction of future slope failures. So this is something that we should try. For swelling expansive soils, actually the research is more advanced, I would say. Currently, it's mainly based on lab analysis, because of geotechnical tests that are very expensive and time-consuming, and soil spectroscopy is actually already known to be good for the evaluations of expansive clays. And here I wanted to show it's a study that was made already, now you see 20 years ago, with airborne hyperspectral data over the Colorado. And there they have huge problems with swelling soils. And maybe to give a scale, here the pixel size is 20 meters. And all the pixels that are identified in red are basically pure monorionite. And monorionite is known to be the biggest problem for swelling potential. So basically, detection and mapping of expansive clays is already demonstrated in different locations and at different spatial scales. There are studies in Egypt, lots in China, I think, and in France. And the advantage is that it could develop vulnerability and risk map and offer practical help to planners to plan on how to build their infrastructure. So last example on land degradation and soil erosion. Here also remote sensing has been a lot used. It's mainly right now based on NDVI time series and looking at changes, and land degradation modeling key variables are vegetation cover and soil conditions. And here hyperspectral benefits is really like very strong and has been already used in several studies based on airborne data. And here you see some test sites where you see different soil conditions, and when the vegetation is growing, basically the vegetation is also affected by the state of the underlying soils. And here we developed spectral indicators, and basically on the right you see we are able to map different stages of soil degradation at the surface. And another thing that is not shown here, but is another big input, is the ability to map this dry and vegetation cover. So especially in dry lands, that will allow to map the vegetation cover and to differentiate more the change of vegetation cover. And I think in general, in the future, we are looking at a synergy between those multi-temporal time series from multispectral data and with less regular but more accurate monitoring from hyperspectral. And thank you for your attention.
Thank you, Sabine. Let's move to the next speaker, that is Eva, please.
Thank you. Okay, so I'm a seismologist, and I would like to talk about rotational seismology today and give you an overview of what that is, how the method works, and some applications with respect to natural hazard and monitoring. My title slide or photo here is from the eruption ongoing eruption in Iceland, because my rotational sensor was actually installed about 5 days before the eruption started. So in general, as a seismologist, we record signals along 3 axes. So they are orthogonal, and we have like a Z component, a north-south component, and the east-west component. And with a normal seismometer, we just record the translation along these axes. So like up-down motion, east-west, or north-south. And we can measure either displacement, velocity, or acceleration with a normal seismometer. This is usually velocity. So velocity in X and Y and in Z. This is what we have. Now recently we have developed some portable instruments which allow us to record the rotational motion as well. So we still have the same 3 axes, but now we do not just measure the up and down motion, but we measure the rotation around these axes. So rotation around Z, rotation around east-west, and rotation around north-south. If we talk about the physics behind it, if we have the translation, we can calculate the curl of the translational motions in order to derive the rotation. So if I have recorded the rotational motion around these 3 axes, it basically acts like a filter, like a wave type filter. Because, for example, if I have a P wave that arrives at my sensor on the left, you can see just a normal seismometer, it will pick up the P wave. If we have a rotational sensor in a isotropic media, the rotational sensor would not pick up any P waves. If there's some conversion, if there's heterogeneities, if there's scattering, of course, there might be a bit of energy that the rotational sensor might pick up. If we look at, for example, the vertical rotation, then this is very sensitive to SH type motion. So we can extract the SH wave motion from it. And so we can learn something about the waves, that compose the wave field, the continuous signal, the tremor, that arrives at the rotational sensor. And if we look at the horizontal motions, they are only sensitive to SV type motion. So this is, for example, a Rayleigh wave. So we already have some means at hand where we can learn more about the properties of the wave field. So one application might be to use a rotational sensor and a seismometer and basically locate them at the same basement. So you have a co-located station, a point measurements of the 6 degrees of freedom. So this is 3 translational motion and 3 rotational motions. So this is pretty cool. A similar setup where we could indirectly measure rotational motions would, for example, be an array. So if you have multiple seismometers, you can install a cluster of them and then indirectly measure the rotation as well. So what can we do if we have a rotational sensor? Well, I already mentioned it's a point measurement, so we can just co-locate a rotational sensor and a seismometer, and we can derive information on the ground, on the source location, and we can study the wave fields. So let's be a bit more precise. So, for example, if I have a source that generates seismic signals, I can estimate the direction of that source. If the source is moving or migrating, I can track the source while it is migrating, just from this one point where I have my sensors. I can derive ground properties, so this might be the phase velocity, or it might be to calculate some dispersion curves across a frequency range. The advantage with a rotational sensor is that I'm not constrained to any frequency band. So if I can just install it and then I realize I'm interested in high frequency signals, or the process that started that generates seismic signals is generating high frequency content, it's not a problem. I can use it. With an array, I'm very constrained to a certain frequency band. If I have a seismometer, in theory, this is just recording translation. But in fact, a seismometer might be affected by tilting. So if the sensor is tilting, the tilting might be recorded as a translation. So it might be good to have a rotational sensor with it to actually check if it's really translation, or whether maybe we need to correct for some tilting motion as well. So if we want to analyze the source of the seismic signal, the rotational sensor adds more information to it, so it might help us to constrain the seismic source better. And finally, you can reduce the number of stations, of course. I don't need 7 stations in an array anymore, but just 2 co-located, so it might reduce the personnel I need in the field as well, or the maintenance costs. So what challenges do I see? Well, there are some technical challenges, which might be the width and the size of the sensor. You can see on the image here an example of a normal seismometer, Trillium compact seismometer, next to a rotational sensor, so it's quite big. The power consumption is currently quite high. And we need to discuss the strength of the signal we're actually interested in versus distance. So if we have, for example, signals from a subglacial flood, these signals tend to be quite small. And then the rotational sensor needs to be very close to it so that it can actually detect it, because it's not as sensitive as a normal seismometer. And then finally, of course, if you're looking into like a large area, you would like to monitor, maybe the price is also an issue in comparison to some other low-cost equipment that is available these days. So some more challenges based on the ground properties might be that the ruptures you would like to study are very complex. Maybe the medium is very heterogeneous. Maybe there are discontinuities, and this all affects, of course, the rotational motions that you might record. Okay, so now I have an example. I mentioned that we can track migrating sources. These migrating sources might, of course, be some, sources linked to natural hazards, such as I already mentioned, subglacial floods. We could track some subaerial floods as well. Maybe there are some lahars in some regions that migrate and that we could track. It could be landslides in the Alps, maybe, it could be avalanches. But also eruptive processes. So I mentioned that I have my sensor quite close to an eruptive site, or potentially lava flows. And the migration source tracking example that we have down here, actually a real example. So some of that like simulations is just synthetic, but a real example is where they tracked actually a car. So see how you managed to track a car just using a rotational sensor and a seismometer next to it. Okay, so this is an example from the ongoing eruption where the rotational sensor picked up a bit of chaos, let's say, around the time when the next fissure opened. So the question is, how does this fissure open? We see, when it opens, just a bit of chaotic seismic ground motion from a different location, and then when it opened, it stabilizes again. And my final slide here is what areas might be affected by a rotational sensor. So where could we actually contribute? Well, I think it could have a big contribution to volcanoseismology, but there are other ones, like, for example, if we think about large N experiments where we have a lot of sensors in the field and we might want to reduce the number of stations and keep, the resolution, for example, of sources. There might be some inverse problem where we want to study the exact processes of how the failure happened. But also locations where the space is limited. So that could be the ocean bottom or other planets or volcanoes where access is very difficult. But especially on the ocean bottom, for example, it's also very important to know whether the sensor is tilted or how it is oriented. So a rotational sensor could really help there. So I'm here for further discussion, but that's it from my side for the moment. Thank you.
Thank you, Eva. Very interesting. Let's now move to the third speaker. We are fully in time. So Gilda, you can take 8-10 minutes in order to finish, and then we will move to the breakout discussion.
Okay, I'm starting to share the screen. Okay, hello. So as you can see from this picture, I mainly work at Etna Volcano. We started this activity in using fiber optic sensing with GFZ and with Philippe Jousset. And today I'll give you a short view about the possibility to use fiber optic sensing as a new tool for natural hazard monitoring. I want also to share with you my view at this moment, which is I am in front of a window with Etna in the front, which is erupting again with a new lava fountain. So from time to time, I'm a little bit distracted by the ongoing activities. And so what about fiber optic sensing? Fiber optic sensing is a very wide application area. And during the last decades, a very increase in technology have been occurred. At the beginning, just fiber optic point sensor have been used. So it means that a remote sensor was placed on the investigated area, and the fiber optic cable were just used to transmit the data. In such a case, we have just only 1 point measurement, very well accurate, but very limited in space. So this kind of sensor could be used to arrange some array sensors, so in an array configuration. But nowadays, taking advantage of the development of optical physics, exploiting the properties of the variation of the light propagation inside a fiber optical cable, it is possible to transform the cable itself in a sensor. And this is known now as distributed fiber optic sensing, which means that each point of the cable is a sensor. So in distributed fiber optic sensor, the fiber itself is a sensor, giving a very high spatial resolution. The distributed fiber optic sensor so allow us for a very dense acquisition of different physical fields, strain, temperature, chemicals, very different observable, which perturb the propagation of the light inside the fiber cable, and at the same time allow us to interrogate the cable over very longer length, which means that it gives us the opportunity to have a very high spatial dense resolution together with a wide coverage. Can be used in harsh environmental conditions, so it is appropriate for geothermal area, for volcanic area. And the most important thing is that the unit which interrogated the cable could be operated in a remotely and safely area. So we can study very remote area just from safely location. Distributed this distributed fiber optic sensor interrogating the cable can be applied not only to dedicated cable, but also to common telecommunication cable, which are already installed in urban area or submarine environment just for telecommunication application. The number of applications and methods are very wide. There are a lot of acronyms around, and each of these acronyms relying on several different devices and different physical optical process which could occur within the fiber. Here I will focus only on the scattering processes, which are the most known one nowadays, which are the elastic scattering and the non-elastic scattering, which occur inside the fiber optic cable. The scattering, both the elastic and the non-elastic, are sensitive to temperature and strain. So measuring the backscattering signal, we can have information about temperature variation or strain variation along the fiber cable. About the elastic scattering, the devices which use the Rayleigh elastic scattering are known as distributed acoustic sensing. This is how it works. So DAS technology is mainly composed by a cable, a fiber optic cable, which is interrogated by a optic reflectometry device, which send a pulse of light within the fiber. And this light, this probe light, is backscattered because of the Rayleigh process, in which the light interacts with the inhomogeneity present inside the fiber optic cable, and the light is backscattered. Mainly measuring the phase change between the probe light and the backscattered light, we can have an estimation about the distance between two scatters. Supposing we have two scatters A and B, and the fiber is stretched or compressed by a vibration. This means that the two scatter A and B change their relative position. Measuring the phase change between the scattered light scattered by the point A and point B, we can have an estimation of the strain, so the new different position between the point A and B. So the advantages of using a distributed fiber optic cable are enormous. We can use already deployed the cable. We can have a very high spatial resolution and a wide coverage. The installation is easy in terms of sensor number per cost work, because the spatial resolution is just a few meters. So installing many seismometer sensor to cover a wide area is not so easy. And one of the most intriguing advantages is that DAS equipment are available to cover and detect low frequency signal, covering the gap between what it is recorded with the traditional sensor nowadays in geodesy and in seismology. Moreover, exploiting the properties of the variation of the property of the light within the fiber optic cable, new instrument concepts are growing. But on the other hand, there are a couple of challenges that we have to cope with. We have to study the coupling issue between the ground and the fiber cable. We have just only single component because we just measure the strain along the direction of the cable. And then we have also to be able to manage a lot of data which will be acquired using this kind of devices because of the high spatial and temporal resolution. So we need the processing software by exploiting HPC facilities. And in a way to have access to urban or submarine area, we also need to deal with the telecom company, which could give us the opportunity to interrogate cable in very remote location. The application for natural hazard are several, and any physical process which generate deformation or ground deformation or vibration and temporal changes are potential application in which fiber optic sensing could be applied. Here I have gathered just a couple of examples of the paper and the study that have been carried out in the last year about earthquakes, tsunami, landslide, icequake. The application in landslides is very peculiar because fiber optics is very easy to be arranged in several configurations. So for example, for monitoring landslide, the fiber could be arranged in an array of sensors like a grid, and 2D movement of the ground could be easily monitored. In 2018, together with GFZ, we started the first application on volcanoes here at Etna, and we deployed a fiber optic cable in several areas of Etna volcano, which is a very complex geodynamic area in which several multi-hazards indeed are interrelated with each other. And in particular, I will show you the application we did on the summit area, where we deployed a 1.5 kilometer of fiber optic cable at a 40 centimeter depth, and the DAS interrogator was installed inside the Pizziden Area Observatory. We have the chance to record a volcanic explosion, a small one, not like the one going today, and we were able to measure the response of the ground due to this very small volcanic eruption. During the experiment, we also deployed some traditional sensors such as a seismometer and infrasound to make a comparison between the new dust measurements to be validated and the traditional one. My time is finished, so we can continue. So later, if there are.
Thank you, Gilda. You can stop your to sharing your screen now. Very interesting talk, and I hope we will discuss now in deep in the breakout session. I just posted in the chat the link where we need to go. Is the link related to the team 4. So I suggest all together, you and people are following us now to join that breakout room, breakout discussion. That is not a room, is a new Zoom link where we will discuss along the 3-stage topic I presented before. So see you there in 1 minute. Thank you so much.
Thank you, Paolo. See you soon.